guess my voice is not very powerful today, so I apologize. I'm sure Alex's voice will be absolutely fine. Hello, and welcome to yet another in our ongoing series of programming languages talks. Today we're very lucky to have a guest speaker talking to us about something that is of increasing interest at Google, static analysis, and specifically static analysis in the context of concurrency. His name is Alex Aiken, and he's been doing a lot of work in this. He's a professor at Stanford University, and here he is.
Thank you very much, Jeremy, and it's great to be here. Thanks very much for inviting me to give a talk. So today I'm going to talk about, well, you can see the title of the slide, Effective Static Race Detection for Java. And my name is listed first, but this is really Mayur Nayak's PhD thesis work, and I'm just here to be the talking head, and all the hard questions I will just defer them over to Mayur. So this is a slide that probably everybody here is more or less aware of, but there's a big change going on today, and actually it's a change that started some time ago, but very recently has really taken hold that the clock speeds have peaked, so the hardware is not going to get a lot faster in terms of the number of instructions that can be issued in a single processor per second in the future. And but the number of transistors have continued to grow. So just because we can't clock the chips faster, it doesn't mean we can't continue to pack more and more transistors onto the chip. And so what vendors are doing about this is they're shipping multi-core processors. Okay, and what does that mean? It means that concurrency is going to be a lot more important in the future than it has been in the past. All right? So up until now, increasing clock speeds meant that even if you just did absolutely nothing, your program ran faster every year. So for no effort, you got a 50% on average increase in performance, assuming you were completely CPU bound, not, I see, not memory. It's all right. It's all right. We'll see. I'm not quite sure well, I'll figure out how to talk to this as we go along. So presumably the slides will cycle back when there's something interesting on them and somebody back there is making a decision about whether to show the slide or not. So no content? Switch to a graphic of the audience. All right? Okay. All right. So as clock speeds kept getting faster, even the sequential programs ran faster. But in the future, the fact that we're only increasing the number of CPU cores means that only concurrent programs are going to run faster. All right. Now, this is actually the fact that concurrency, the fact that we do more concurrent programming, or the fact that concurrent programming is an interesting topic. This is not something new. Everybody, people in this audience have probably been well aware of this for a long time. And here's the standard baby example of why reasoning about concurrent programs is not so easy. So here's a place where we're doing an update. Let's just review for anybody who doesn't know this stuff. And what we do, well, if we want to increment x by 1, we have to do a load. We do the increment, and then we have to do a store. Okay, so the temporary here is supposed to suggest that this is something that lives in some kind of local storage, like a register, and this is something that's out in some kind of shared storage, like main memory. And so we do one possible execution of this, or the only possible execution of this, we do the load, the increment, and the store. And if we have another thread that does the same thing, using a different temporary, but using the same shared variable, then here's one possible ordering. There's another possible execution sequence. And these are the two that we would like to have. But then, of course, there's all kinds of other execution sequences. If the unit of atomicity here of single instruction execution, we can get interleaving like this. And the problem is that in the first two cases, we get the expected result where x has been incremented by 2. But in the last case, and in many of the other cases, if not all of them, we get the wrong answer. Okay, so we actually lose one of the updates, and x comes back as the wrong value. All right. So I got to position myself here a little better with respect to this wireless device. All right. So a race then is when we have the same location accessed by different threads simultaneously. So you have some shared location accessed by two threads, and at least one of those locations is a write. Okay. And the simultaneous here means that there's no ordering constraint imposed by the program. It's actually possible for these things to happen at the same time. Okay? And so race conditions are a particularly insidious kind of concurrency bug. And it's triggered under non-deterministic circumstances. You don't, because this depends on the thread scheduler, you don't know just because the program works once, that doesn't mean that if you run it again, it will work the second time. And the second problem is that there's no fail-stop behavior. So meaning that in a lot of cases, when you encounter a bug, something like a null pointer dereference, the program just stops. Okay, so even if the bug itself might be triggered non-deterministically, I mean it doesn't happen in every execution, not repeatably, at least when it does happen, the program actually stops running. That doesn't happen with race conditions. So the program will just keep happily executing along, and who knows what will be the final result. So you won't discover the error, if you discover it at all, until far after the time at which the error actually occurred. All right, and of course, race conditions have been something that have been studied for a long time in concurrency theory and practice. All right, and it's actually not just race conditions where this problem comes up. So actually, the notion of a race occurs in the formulation of many other properties you would like to talk about with respect to concurrency. So for example, if you want to check atomicity, if you have atomicity declarations in a program, checking whether these atomicity declarations actually make sense boils down to a race detection problem. Similarly, for deadlock detection, to do deadlock detection, you actually need a race checker. All right? And I think it's pretty well known that concurrent programs today are just riddled with races. All right? So pretty much you can pick up any concurrent Java program, and you're going to find race conditions in it. Okay? At least any concurrent Java program of significant size. All right. Okay, so let's come back to our example. And as we said before, the same location, what was the condition under which we actually had the race? The same location has to be accessed by different threads simultaneously, and at least one of those accesses is a write. Okay, so in this case, the write to the shared variable x. All right, and then there's the other one is the read of x. So here we have we have a race between this write, and between this read and this write, and also between that read and that write. Okay, those are all the potential races in this little fragment. Okay. All right. Now, so let's refine this condition a little bit. So we say the same location has to be accessed by different threads simultaneously without holding a common lock. Okay. So instead of just talking about sort of general accesses, let's focus on the lock-based synchronization discipline. So the most common way of controlling access to shared locations is through locks. And the stuff I'm going to talk about today is all about doing this only in the presence of locks. Okay, so we're not going to look at other synchronization idioms. Okay, so now let me talk about some previous work. So this is not a new problem, and what I would really like to do, but I see I can't do it because there's tape on the floor indicating this thing has to stay in its current position. All right. So I will stand here and do my best to focus on the slides while also facing you. So maybe I should actually use the lectern like a lectern and stand here. How's this look? Okay, that's good. All right, so there's a fair amount of previous work on this going way back. Okay, and this is all about race detection. And if you go back in the 1980s, there was a fair amount of work. The 1990s, all that kind of work picked up. Since 2000, there's been even more. Okay, and it just goes on and on and on. All right, so I hope that most of what I've said here so far has been stuff that's all relatively familiar to you, although perhaps there were one or two small things that they hadn't seen before. And the bottom line observation, if you were to summarize all this work from the point of view of tools, is that none of the tools that have been proposed actually do very much in practice. So if you actually turn them loose on real code, they will find some races, but very few, actually, and far fewer than we expect to actually see in these programs. All right. And here's a brief overview of our results. So this is looking at relatively mature Java programs. It's all open source stuff, so large open source Java programs, and I'll tell you which ones we looked at specifically in a little while. But if you take all the work published in the last decade and you add up all the bugs reported in those papers, and then these are the ones from the work that we've done in the last year or so, and we just have a quantum change in the effectiveness of the tool. So that's why the title of the talk is Effective Static Race Detection. Now there are some new ideas, and I will tell you what those are. There are also a lot of old ideas in Cord. So all this stuff that went before, we certainly built upon it and used a lot of the concepts that people had previously discovered, but we've put them together in a new way. And we've also filled in some holes, and I'll tell you exactly what those were. And there's some key things that the previous approaches weren't doing that turned out to be important. All right. Okay. So what's our approach to race detection? So we're going to do, yeah, go ahead. Sorry.
The question to this previous slide. So
yeah.
On the left, bar for the previous work, if you also include dynamic.
Want to go back one more?
No, the one with the bars. So for the previous work, if you also added dynamic techniques, would it be going a little bit higher, you think?
It would go a little bit higher, but not a lot. Okay, you want?
It includes both static and dynamic.
Yeah, so this bar here is supposed to include both static and dynamic, Mayura says. I wasn't quite sure if we had the dynamic techniques in there. There are, so the answer is no, wouldn't move at all. And the reason for that is that the dynamic techniques, so why don't the static techniques, I'll just foreshadow things a little bit. So the problem with most of the static techniques, besides being incomplete, meaning they're not sound and guaranteed to find all the races, which we are, all right? In addition, most of them don't work on large programs. So there's just a scalability issue. And if you can only push a small amount of code through the tools, that really limits the number of issues you can find, okay? The dynamic tools don't suffer from that problem, okay? They can, dynamic tool, you can run it on, you can do the instrumentation, and in some sense you've succeeded at that point. But in order to actually find the races, you have to run the thing, okay? So you have to have workloads, and you have to be able to run it for a long time, and you have to be able to run it under lots of different thread schedules in many cases with some of the tools in order to find it. And that's just a huge amount of work, to find those workloads to actually drive the tool well enough to find the bugs, even in the case where they're sounding complete, which a lot of them are not, okay, where they're not going to find all the bugs. Just the amount of data you have to run the programs, you're only going to get limited coverage. And so in practice, they don't find very many bugs either. Okay. All right. So our approach is to take, first of all the potential races in the program. Okay. And what that means is all the pairs of reads and writes in the program that could potentially race. So say take all the reads and writes to the same field of a given type. And we want to narrow that down to the set just of racing pairs, meaning the actual set of races in the program. Okay? And this diagram is meant to suggest that there's a big gap in between. I mean, there's a huge number of possible potential races in the program and only a very small set of things that actually would race. Okay, so what are the challenges in doing this? So one challenge is that the same location can be accessed. So what's our criteria again? So our criteria is that the same location is accessed by different threads simultaneously without holding a common lock. Okay, so that's the specification of what we want to check. All right, I'll repeat it one more time. Same location accessed by different threads simultaneously without holding a common lock. Okay, and so we have to handle multiple aspects. That specification actually turns out to be a complicated thing to check. So, and we're actually going to break it up into several different analyses. And one of the things about race detection that makes it complicated, compared to other kinds of static analysis or bug finding tools, is that actually the specification of a race is itself a very complex notion. Okay, it isn't just a single property. It's actually the composition of several properties. Here are three of them. Okay, that come straight out of this formulation of the specification. So we need to detect whether two threads are accessing the same location. We need to detect whether they're actually different threads. Okay, it doesn't matter if you access the same location within a single thread. And we need to know that this can actually happen without ordering constraints. We need to know that it's simultaneous. Okay? So all of these things relate to the precision of the analysis, okay, at least the way we would cast it. Okay? We will view these things as all precision issues. And essentially, whatever kind of static analysis you have, it needs to do a good job on all three of these things, or you're going to have lots of false positives slipping through, lots of things that are potentially look like races, but in fact are not. Will get by, and that will water down your results. And what we showed now a year ago is a very precise May alias analysis. So essentially, an alias analysis that tells you when two expressions might refer to the same memory location. Is really central to solving these three problems. Okay? And people had tried this before, actually using May alias analysis to solve these three problems, but their notion of precision wasn't quite the notion that turned out to work really well for us. Okay? And I'll tell you a little bit more about that in a little while. And the false positive rate in this work was about 20%. So when it would report a race, it was a 4 in 5 chance it was actually a race. Okay? And yeah. So the question is whether we're using abstract interpretation. Is that okay? And the answer is we're using static analysis. That's a term I prefer to use. So abstract interpretation has there's two interpretations of that term. Okay, one is it's a general theory of static analysis that covers pretty much everything. Okay, so in that sense, yes, we're doing abstract interpretation. All right, and I'll show you a little bit more about how exactly we solve these three problems as I go along in the talk. There's another interpretation of static analysis, of abstract interpretation, excuse me, which is as a specific collection of algorithms. There's a specific cookbook recipe for constructing program analyses that people often use, often associate with the term abstract interpretation. And we're not doing anything like that. Okay, so this is a very different way of, we're not doing a kind of glorified data flow analysis here. We're doing something that's quite a bit more sophisticated than that. All right? Okay. All right, so then the second thing that we did, or the second big thing we did, was to try to figure out how to correlate locks with the locations they guard. Okay, how to figure out which locks guard which memory locations. And this is key to the last bit here, figuring out whether there's a common lock held when you are checking a pair of accesses to see if they might race. Okay, and this is much more of a soundness issue. All right, so for this, you need to do this well in order to guarantee that you're going to find all the races. Okay, and this was a big stumbling block in previous work. And the big idea here, which I'll spend quite a bit of time talking about today, was something called, or is something called conditional must-not alias analysis, which was published just earlier this year. And this is the idea that allows us to analyze the locks precisely. Okay. And the problem that it solved, for those who are familiar with it, and I'll actually say a bit more about this, but not a lot, is that it circumvents the apparent need for what's called a must-alias analysis. All right, so now back to our big picture. So we have the set of all pairs, and we want to whittle that down to the set of just racing pairs, just identify exactly the set of races. Okay? Yeah, is there a question? I thought, is that somebody else somewhere? Okay. So we're going to do this in a series of phases, corresponding to each of those little pieces I showed you on the previous slide. So we're going to have one analysis that's going to figure out what the set of aliasing pairs is, okay, so using the alias analysis. And then the things that could be shared across threads. And then things that could actually execute simultaneously, call those the parallel pairs. And finally, analysis of the locks to find out what locks guard which locations. We call that the unlocked pairs. And that unlocked set of pairs, the last stage of this analysis, and whittling away at the total set of possible racing pairs, notice that this is, there's still a gap between the racing pairs and the unlocked pairs. There is a false positive rate, and it remains about 20% in this work. Okay, so in the final version, which is guaranteed to find all the races, and about 4 and 5 of those will be actual races empirically, and 1 and 5 will be something that's not a race, but the tool was just confused. Okay? All right, so now let me tell you a little about each of these phases. And I'm not going to go into any kind of detail about most of these. All right? If you want to stop and ask me questions, I'd be happy to talk about more, give you more information. But this is at a very, very high level, just because there's not going to be time to give you all the details. All right, so now we have 2 generic threads here, thread 1 and thread 2. All right, and we're using Java-style locking, okay, where there's a synchronized construct that acquires the lock. And so locking in Java is done by every object can be a lock. And so in this case, we acquire the lock on object L1, and then we have some kind of access here to a field. Similarly, in thread 2, we acquire a lock on some object L2, and we have an access to the same field, but possibly of a different structure. Okay. Now, so when is this particular pair going to be race-free? Okay. Well, one possibility is that E1 and E2 never refer to the same value. Okay. If E1 and E2 never refer to the same value, then there's no race. I mean, these are 2 independent threads that are accessing different parts of memory, and so there's no race condition. And that we can write that in standard kind of program analysis terminology as saying that E1 and E2 must not alias. All right, so an alias just means that 2 expressions may potentially refer to the same memory location. If they cannot alias, then they can't be race. Now, must not alias is actually not quite the standard term that people use. The way people actually usually compute that is they compute a may alias analysis to figure out first which pairs of things might refer to the same location. Okay? And then the complement of that set are the things that can't possibly refer to the same location. So if 2 things cannot may alias, then they must not alias. All right? All right. Okay, so now let's talk a little bit about May alias analysis. All right, so this is a huge topic. All right, so anybody who's done any work in static analysis has come across this. And if I were to do another slide comparable to race checking, like the one I showed you before of all the previous related work, it would look very similar. Okay, it would start a little later. All right, it would start about the early 90s, okay, instead of in the late 80s. But then it would be very, very crowded from about 1997 on, okay, with multiple papers in all the major conferences each year, right up to the present day. Okay, so it's still a hot topic, okay, and it seems to be a very, very difficult problem. Now, so what are the big ideas in May alias analysis? Well, big idea number one is context-insensitive analysis. All right, and all this. So what would we do in a context-insensitive analysis? We would do the following thing. First of all, you can't reason about all the possible memory locations that a program allocates. All right, this is one of the fundamental barriers in static analysis. So when the program actually runs, there's an awful lot of locations. Okay? But the thing is that static analysis isn't even reasoning about a single execution, it's reasoning about all possible executions. So even though in any particular run the number of locations might be bounded, over all possible runs, the set of locations is truly infinite for arbitrarily large inputs, for example. All right, so we have to have some kind of abstraction. We're going to glom together multiple program locations into a single abstract location. And the standard context-insensitive way of doing this is to say the abstract value is going to be the set of allocation sites. I will just identify every value with the site where it was allocated. And there's only a finite number of allocation sites in the program. And so I can identify some classes of values by their allocation sites. All right? So in this case, what would I be able to say? I would be able to say that E1 and E2 don't alias, okay? They don't alias if the possible sites where E1 was allocated intersected with the possible sites where E2 is allocated is empty. All right, so I have to do some kind of global analysis to figure out what the possible allocation sites are of E1 and E2. So I have to stare at the program and compute flow relationships to figure out where stuff that's allocated at a given site might go, all right, in all possible ways throughout the program. And eventually I get an estimate for every expression in the program of where each of those expressions might have originally been allocated, where the new expression was that allocated them. And if the intersection of those two sets happen to be empty, well, then I know these things can never alias because they're talking about things that are allocated at different syntactic sites in the program. All right? Now, it turns out that idea number one is just a terrible idea. Okay? I mean, it's a good starting point, but it's not nearly accurate enough for almost anything you want to do in software quality. Okay? Actually, it's not a bad idea for program optimization. So for program optimization purposes, context insensitivity is sometimes enough to give you enough distinctions that you can do more compiler optimizations than you could otherwise do. All right? But for almost any kind of non-trivial property that you want to prove in terms of the semantics of the program and whether it has a bug of a certain kind, context insensitive analysis is very rarely enough. All right? So big idea number two is to do, well, if it's not going to be context insensitive, it must be context sensitive, whatever that is. Okay? So, and the standard technical term here is called KCFA, all right, for various levels of K. And the battery in this thing must be going. And so what we're going to say here now is that for context K equals 1, we're going to distinguish values based on the call site. All right, so we'll distinguish values based on where functions are called from. So in this case, I have E1 is calling Baz, and I have E2 as dispatch also to Baz, but they're being called from within different functions. All right, and I can make a distinction saying, okay, well, now I know now a little bit about the call stack in which this function was executed, and I can use that to make more distinctions in the analysis than just the allocation site. All right, so in this case, we would analyze the function Baz in two different contexts, right? And we would be able to keep track, we would be doubling the number of program points that we could talk about. So we would keep track, we'd be able to analyze Baz completely, these two instances of Baz completely separately from each other, all right? Now, that turns out to be a pretty good idea, okay? And this has actually been shown to be useful in a lot of settings for various kinds of properties. But generally speaking, I mean, it's certainly better than context insensitive. That's probably what I should say. So people realize pretty early on this is way better than just being completely context insensitive. But generally speaking, the next problem you run into is that you either have too few still contexts, meaning that somehow the number of distinctions you're making is not enough. Too many things are still being glommed together to make useful distinctions. Okay, so all the infinite sets of objects in the heap, too many of them wind up in the same bucket, and you just can't distinguish two things that you really need to distinguish. Or you get too many in the sense that your tool doesn't terminate. Okay, that you start to build up the number of contexts very rapidly, especially as you go to k equals 2, 3, 4, keeping larger and larger portions of the call stack in which you analyze all these different procedures. Okay. All right. So there's another idea, which is object-sensitive alias analysis, which is analogous to context-sensitive analysis, but focuses not on the call stack so much as on the allocation history of objects. And this is a recent alias analysis that was introduced by Milanova and Reiter a few years ago. Okay. And what we're going to do here is we're going to change our abstract values now to be strings of allocation sites. So instead of just keeping track of a single allocation site, we're going to keep track of a string of allocation sites. And what's the particular string we're going to keep track of? It's going to be the, well, I'll just tell you what for k equals 1. So for k equals 1, the allocation site that we're going to keep track of, the string is going to be just a single allocation site. It's going to be the site of the this parameter. All right, so where was the this parameter allocated? Okay. And, oops, back up. And so now, here, we will still analyze BAS here in two different contexts because we have two different this parameters here. Assuming these are actually distinct this parameters, we'll actually get two distinct contexts for BAS based on what based on where they were allocated. All right. And that will allow us to, to associate different information for BAS for objects that were allocated at one site and distinct from information for BAS associated with objects that are allocated at a different call site passes of this parameter. And the intuition behind object-sensitive analysis is that it's going to do a good job of separating out data structures for us that are allocated in different parts of the program. So think about a hash table. Okay. So a typical hash table will have multiple levels in it, and it'll be allocated by some hash table package, right? So at the root, you'll have something that's a handle, a container on the entire hash table, and then below that, say, will be the buckets, and below that will be the individual elements. So there'll be 3 levels of objects, say, in a typical hash table. Now, if I use hash tables in multiple places in the program, the same hash table, okay, same hash table package being used in different instances, and I create new hash tables all over the place, I would really like those hash tables to be separated because I'm probably not using those hash tables for anything remotely the same. I might have one hash table that's holding user information, another hash table that's keeping track, say, in a search engine of various words that I'm searching for, some sort of index structure like that. Okay, and these happen to be allocated by the same hash table structure, but they're just completely different purposes. All right. So if I was keeping track of object sensitivity to k equals 3, then I would actually distinguish those 3, okay, intuitively, because the 3 levels of objects that are being allocated are all allocated by each. I call the new function on the root of I create a new hash table, and then it creates these other levels 2 levels deep, and that will distinguish. And it happens that the way object sensitivity is set up that this string that I will keep track of is exactly that string of 3. Okay, the root, the buckets, and the leaves. All right, and then the 2 sites, the 2 hash tables in 2 different parts of the program will be kept separate. All right, so object sensitivity turns out to do a very good job of capturing exactly the notion of different data structures allocated in different same type of data structure allocated in different parts of the program. It keeps track of that more economically than KCFA does, than the context sensitivity does. So no scalable implementations for object-sensitive analysis for even k equals 1 prior to our work. And the basic insights into making this work out well is to have a symbolic representation of the relations. Okay, so we use BDDs to represent the alias relations. And then we added to that a demand-driven race detection algorithm. So actually, we refine this, the amount of sensitivity we use based on where we see races. So we start out with k equals 1 for the entire program. Okay, analyze the program that way, see what races the tool reports. Then if it turns out that we have races in certain places, we try refining those allocation sites to k equals 2. All right, that gives us more precision. Some of the races go away. Now there's fewer races left in the program, and we keep repeating that until it converges, until by increasing the sensitivity, we don't eliminate any more races, and that's where we stop. Okay? So some parts of the program are modeled more precisely than others based on where the races appear to be, and this allows us to go much deeper with the alias analysis than we normally would. All right. So we see in our experiments that we need sensitivity up to k equals 5. That's actually useful to have object sensitivity up to depth k equals 5. We don't, and I assume that if we look at even larger programs, we would probably need more than that. But this is still tractable if we're doing it for only a few sites in the program. Is there a question? Yeah.
So do you, in your approach, do you set the same k for the whole program, or do you adaptively use different lengths depending on your data structures and only more or less specific?
I'm sorry, I couldn't understand.
Would you adaptively perhaps choose different k for different data structures in your program depending on how much they need? If for one of them it is ambiguous for k equal 1, there's no point in increasing it to 5, right?
Right.
For another one may, so do you do it adaptively this way?
Yeah, we do it adaptively, just like, so the question was, do we do it adaptively? Do we actually alter the sensitivity adaptively in response to what, I assume, into what we see? And that's exactly what we do. So we start with k equals 1, and if that's sufficient to prove that there's no race on a given field, then we just leave that at k equals 1. But if there are still races being reported in other fields, then we increase the sensitivity there and rerun the analysis with a higher sensitivity just for those fields. Okay? All right, so back to our picture. Okay, so here's where we are. All right, so now how can we use this alias analysis for race detection? So field F is going to be race-free. We said if E1 and E2 never refer to the same value. So if the May alias relation between E1 and E2, however you compute that, if they can't, if it turns out they can't alias, then you know that those two expressions can never race. But there's another possibility. Okay, this is only half the story. This is one way that things might be proven race-free. All right. The other way that they might be proven race-free is if the locks are always guaranteed to be the same. Okay, so let me just repeat this. So at this level, if you have a May alias analysis, however you got one, okay, and we have one that is good in certain ways and works well for this application, then you can discharge some number of the races just by proving that those expressions can never access the same location. Now, if it turns out that your May alias analysis doesn't succeed in proving that, if in fact the May alias analysis says that, well, they might access the same location, then it could still be race-free, provided that these locks that are acquired here in the synchronized blocks are always the same, because that guarantees mutual exclusion. Because now if they're accessing the same location, it doesn't matter because there's guaranteed to be some kind of ordering on the constraint. Okay, so one of these two things, if either of these two things is true, then you can prove that that particular pair of accesses can't race. All right, now that, however, is a must alias analysis, okay? Because here it's always referred to the same value. All right? So that means that L1 and L2 must alias. That means in every execution, they must be the same location. Not just might be, okay? Because if they might be the same location, well, then they might be different, and then you might have a race, okay? So that makes you have to be able to guarantee that they're always going to be the same. All right? So must alias analysis, if you go back and drew a slide of all the work on must alias analysis, I think it'd be like 3 papers on it or something like that, because it turned out to be a much, much harder problem. Nobody's had a really good idea about how to do it in a very general way. And it's not really clear how it would be useful, because it kind of, even if you could solve the problem well, it's not clear that that things must alias very often. Okay, so it isn't that common that things actually must alias at all. And so this has been an impediment to many previous race detectors. Okay, and this is probably the reason that there's some folk wisdom around the static race detection is intractable. In fact, most of the activity in static race in race detection over the last few years has been in dynamic race detectors. Okay, and our insight here, the main idea, and this is the thing that's probably the most new, is that must alias analysis isn't even needed for this problem. In fact, that formulation I showed you on the previous slide, you don't need that formulation. There's a different way to formulate the problem that gets around the whole need for talking about must alias analysis. All right, so let me show you that. Okay, so the new idea is something we call conditional must not alias analysis. It would be nice if we had a sexier name for it, but it at least says what it actually is. So here's the statement. So field F is going to be race-free. The condition is going to be that whenever L1 and L2 refer to different values, E1 and E2 also refer to different values. Okay, so what does this say? This says that if L1 and L2 are different locks, all right, when you enter these two blocks, then it has to be the case that E1 and E2 refer to different pieces of memory. Okay? And if that's true, if that condition is true, then your program is race-free. All right? Or at least this pair is race-free, I should say. Now, if I formalize that, we can see that it doesn't involve must-alias analysis at all. It says that if L1 and L2 must not alias, that should imply that E1 and E2 must not alias. Okay, so under the assumption, so notice what's going on here. This is just must not alias analysis. I mean, it's the only building block I'm using. But now there's an implication here, meaning that in the proof of must not aliasing over here, I'm allowed to assume that these two don't alias. All right, so I can get some assumptions for free that I can add to my knowledge of facts about things that don't alias, and I can use that to prove more things don't alias. All right? And there's no must alias information required. So here's an example. Okay, and we'll spend a fair amount of time on this. This is a real first and probably only a really concrete code example other than the trivial one at the beginning. And so what does this piece of code do? Well, we allocate a new array. All right, we'll just name it by this. We're just going to name things here by allocation sites. So I'm going to be a little abusive here about syntax and say we're going to name things H0, H1, and H2. That just points to those three allocation sites. So we allocate an array, and then we fill in the elements of the array with new objects in a loop. Okay, and all the elements of the array that are getting filled in there are of type H1. And then the G field of type H2, the G field of type H of each one of those H1 objects gets a new H2 object. Right, and then we go around the loop and do that a bunch of times. And so we get a bunch more things that look like that. So we get some sort of structure that looks like this. Okay? All right, this is similar. This is the three-level structure I was trying to describe before by waving my hands in the air. Here it is concretely on a slide. Okay? So now, let's take a look at a generic way of accessing these two, various ways of accessing this data structure that might lead to races. Okay, so let's say I have a thread that's executing the same piece of code here. All right, let's say, but I'm going to, just so I can name the two different things differently, this piece of code, calls the element of the array, it grabs x1, this one calls it x2, and then they synchronize on something, and we'll look at different possibilities for that in just a moment, and then they go off and do some kind of write, and what they're writing to is a field of this H2 object. All right, but they're accessing the H2 object from the root. So they're taking X, they're going from dereferencing A, and then a field G of one of these objects in the container, and then a field F of that object at the leaf, H2. All right? Okay, so now let's look at three different cases. So here's an easy case, coarse-grained locking. All right, this is the standard pattern where you just acquire a lock on the entire data structure. It's basically you lock the whole world, do your operation, and then you unlock the world. All right, so if you have a database or something like that, you lock the whole database, go and write one record, okay, and then unlock the whole thing. All right. So here's our condition. So field F is going to be race-free, and then here I've just copied out the condition. So now let's instantiate that condition with the particular situation we're in here. All right. What this would say is that if A must not alias A implies that x1.g doesn't alias x2.g, then this thing is race-free. Okay? And so this is actually a really easy case because this is false, right? A always aliases itself. And so false implies anything, right? So clearly if you lock the whole world, there can't be any races, right? So there's nothing, so remember what the condition said before. It said if these two locks were different, then we have to prove something about the memory access. If the blocks are always the same, there's nothing to prove. We don't have to do anything. Don't have to do any work. Okay, so that's true. So coarse-grained locking is really easy to prove, as it should be. All right. Okay. Well, so that was easy. Let's try a different one. So let's look at fine-grained locking. So the other extreme is every time you want to access something in the structure, you lock at the finest granularity possible. So if you want to lock the, instead of locking the entire database, you lock the individual record, you update that record, and then you release your lock. Okay. So what would that correspond to here? Well, you're going to lock the H2 object. So you're going to sync on the H2 objects, all right? And if we look at our condition again, what's going to happen to it? So it would say that if x1.g does not alias x2.g, can we prove from that that x1.g does not alias x2.g? And that seems like something that's very likely to be true. Don't have to have very complicated reasoning to figure that out. Okay, so that also is trivially true. So the coarse-grained locking and the fine-grained locking cases both fall out as really easy cases from this definition. And that makes sense. I mean, just to go over the fine-grained locking again, so here's the mathematical formulation, but intuitively what it's saying is that if I lock an object and then modify that object, well, nobody can race with me. Okay, if I'm just locking the object that I'm modifying, nobody can get in there and do anything with it while I'm doing the modification. All right? Okay, so where does it get interesting? So the hard case is the medium-grained locking case. All right, so what are we going to do in this case? We're going to lock, well, actually, let me review. Why would we ever want to do anything other than coarse-grained locking or fine-grained locking? Well, coarse-grained locking obviously doesn't allow a whole lot of concurrency. A lot of systems start out that way, and then they run into a problem because you can't get very many concurrent things going, and so they switch to some other locking style. So the Linux kernel, for example, started out with only one lock, the so-called BKL, the big kernel lock. All right? And as soon as the project got as soon as the project got to a certain stage, they had to have more locks and lock at a finer granularity. The problem with the very fine-grained locking is that it's very expensive to acquire and release all these locks. Okay, so you get a lot of concurrency, but you have a lot of overhead too per unit of concurrency, and there's diminishing returns in locking at too fine a granularity. So everybody wants to lock at some kind of sweet spot in the middle. All right, so the medium-grained locking case would be instead of locking the whole structure, you just lock one of the buckets. Okay, and then you can go off and modify the things underneath that, so you can get concurrency at this level between multiple accesses coming in at the different H1s, but you have exclusive access to all the H2s underneath. All right? Okay, so what happens in this case? So here we would have to, in order to prove that this field is race-free, we'd have to show what? So there's the generic condition. Here it is instantiated. So we have to show that if x1 and x2 are different, okay, meaning that if x1 and x2 refer to different H1 objects, then in fact x1.g and x2.g are different, that we're guaranteed to be accessing here different H2 objects. Okay? Now, so there it is in English, field G of distinct H1 values. So this will be true if field G of distinct H1 values are linked to distinct H2 values. And for this particular data structure, that happens to be true because of the way we built it. Okay? So in fact, that's OK. Now, but this is a heap property, okay, or a shape property of the data structures. All right, and this is actually something that static analysis tools and compilers and all kinds of other language-based tools are usually typically terrible at reasoning about. So anytime you want to reason about something that's in local variables, you can do a lot. Okay? As soon as you start talking about stuff that's in the heap, it gets much, much harder. But it turns out that this particular shape property, or we need this kind of single access property that everything from one kind of data structure, one kind of value linked to another kind of value is uniquely reachable. This kind of thing, it turns out that actually in practice we can reason about this. Okay, that it's a very limited property actually, and the way we set it up, it turns out that in practice we can actually do this kind of calculation. So let me show you how we do that now. Okay, so we call this disjoint reachability, and the thing we want to prove is that from distinct H1 values, we can reach via one or more field accesses only distinct H2 values. All right, so the generic picture looks like that. Okay, over on the right, that's the kind of shape we're looking at trying to prove exists in a program. And I'm just going to introduce a little bit of notation here. We're going to say that the set H2, the allocation site H2, is in the disjoint reachability set of H1 if this holds. So if I pick distinct values out of the distinct values allocated H1 out of a bag, then from those two values, I can only reach distinct H2 values. Those two distinct H1 values can never share an H2 value via one or more accesses, either immediately or transitively. Okay, and we'll just notate, if that's true, we're just going to write it like this. So we can talk about the disjoint reachability set of a given allocation site. Okay, what other kinds of types are going to be disjointly reachable from that place? Okay? All right. Now, here's the picture. So I'm not going to show you how we calculated that, but I'll show you how we use it. If we can calculate disjoint reachability, okay, which is a completely separate problem, and I'm not going to tell you how we do that, although you're welcome to ask questions that I can't answer about it if you wish. But I'm going to show you how we use it. So given that we can compute disjoint reachability, how would we use that in this conditional must-not alias analysis? All right? So if I take the definition here of must-not alias analysis and I plug in now what I need to do, it looks like this. Okay? So we have a diagram that looks like that. All right, so what we're computing here, these are the allocation sites of E1, the allocation sites of E2, the allocation sites of the lock, of the two locks, L1 and L2. All right? So now, what I'm saying is, where can we potentially have a race? Well, the only place where we can have a race is on the intersection of these two sets. Okay, because that's the only things they share in common. So wherever E1 and E2 might be the same object, that's where we might have a race. Okay, so that's why we have sites of E1 intersected with the sites of E2. Okay, those are the potential races. So everything in here is potentially dangerous thing that we have to be sure is protected properly by locks. Okay? So these things ought to be in a disjoint reachability set of something. Okay? So if all the stuff that's in the intersection of these two things is disjointly reachable from anything that could be in one of the two locks, so the union of those two sets, okay, then this is guaranteed to be race-free. All right? Okay? Yeah.
Are you assuming that locks are, that the object you're locking, you can actually reach the field you're accessing from the object you're locking?
Yes, we are. Yeah, so there's a question whether we're actually assuming that you can reach the object that we're accessing from the lock. All right, and we are definitely assuming that.
Isn't that kind of a big assumption?
It doesn't seem to be a big assumption in practice. This is the standard pattern. This is actually the standard pattern. Yeah, so here it is right here. E1 is reachable from L1 and E2 is reachable from L2. Yeah. And so we are assuming this. We could relax this. So we actually know how to relax that condition. Okay, we actually could do a better job, but it hasn't been necessary so far. At least in the benchmarks we've looked at, that hasn't been an issue. All right, but yes, I mean, and so in particular, we're assuming that the object that you're accessing is under the object that you're locking. Okay, that you're not locking something below and then accessing a parent, say.
So another common, and we won't go into this, another common pattern is to have a specific object that you create that is a lock object. That pretty easily extend this to the exact pattern.
So the implementation does handle the backward case of example. Okay, so
Yeah, that one.
Yeah. Okay. All right. So the hard case then, coming back to the medium-grained locking case, let's look at this particular example. So we're going to say field F is race-free. We have this situation. Okay. And if we plug into the definition, the sites of X, the sites where x1.g and x2.g are allocated is a subset of the sites in the disjoint reachability set of the sites where x1 and x2 are allocated. And that's just saying that x1.g is H2 in the disjoint reachability set of H1, okay? Which we already said before, all right? And so we have, as I said, I'm not showing you how the analysis of disjoint reachability works, but we have a separate analysis that computes these disjoint reachability relationships, and this one is true, and so we'll be able to prove that this is race-free, okay? All right, so let me tell you a little bit about our experience so far with the tool. So we've looked at 12 multi-threaded Java programs, and including some very large ones and some very, very small ones. And the small ones we picked because they were used in previous work, just to validate our results against previously reported results. And one thing that's good about Chord, one of the advantages of a static tool over a dynamic tool is that you can actually do checking on libraries. So before you have a complete program, if you just have a client, if you just have a library and no client, then you can still look for races there. So the tool works with open programs. It doesn't need to have a whole program analysis. Okay? So there's all the tool output and the threads of discussions with the developers are on the website, on Mayor's website. And actually, this is all work that he did. So all the conversations with developers and answering their questions, it's all part of the record, and it's all due to him. And let's go on and look at the actual numbers. So here are some of the benchmarks that here are the benchmarks that we used. The ones above the line here are the ones that were used in previous work. Okay, these are the smaller ones. The ones below the line are the ones that we added just because they were available to us and they were bigger, with Apache Derby being by far the largest. So this is an open source relational database management system written in Java. It's actually just the library. It's not a full application. Okay. And here's the time to do the analysis over here. And these numbers are fairly old, aren't they, Mayur? So what's the current times like? About the same? Yeah, so the times haven't changed significantly, but this is a minutes, not hours, and this is not seconds, okay, but it's minutes and it's not hours as the scale of the analysis. Okay, here's the little chart showing the effectiveness of the various phases and how many pairs are retained after each stage. So you can see that aliasing in particular cuts down a huge number. This is, I should point out, this is a log scale chart. Okay, so big drops here are really astronomical drops in terms of actual numbers. And then the other phase that does an awful lot is the last phase, the analysis of the locking. Generally, there's a big gap there. Okay. Now, the racing pairs, these are the actual races in the program. That's done by hand. Okay, so we take the red bar, we look at or Mayur looks at every one of those by hand, decides whether it's a real race or not, and then anything. So the difference between the red bar and the white bar are the false positives. Okay, and the other phases, some of them, there is some program where every one of those phases makes a big difference. Okay, so they're all necessary. There are plenty of examples like over here where none of those other phases makes a huge difference until you get to the last one. All right. Yeah.
So for the Derby, there are about 1,000 cases that you look at manually.
Yes.
How much effort was that?
That was almost a week, actually, which is why we have just one large program, because they typically have so many races. And in some sense, races are not a good property to check because you have this quadratic blow up in the property itself. So it took 1 week.
Yeah. So the question was, how long did it take to analyze the 1,000 races in Derby? And the answer was about a week. All right, here's the classification of the unlocked pairs and what we learned from them. So one thing about races I didn't mention at the beginning is that not all races are bad. Just the vast majority are bad. But races by itself are usually, so it's a little bit of a low-level property. And there are places where programmers use races on purpose. So some small number of these races are benign, meaning that they are races that were probably there intentionally or that nobody would care about them. So you can see here's a column with the analysis of the benign races. And then there's the analysis over here of the ones with the false positives. Okay? And then finally, over here is analysis of the number of bugs. And the number of bugs is always less than the number of races because usually a race will exhibit itself in many different ways. There'll be lots of different ways to reach the two expressions that actually race. There'll be many different call paths along which you could come. And because of the context-sensitive analysis, the object-sensitive analysis, each one of those possible different ways can get reported as a separate race. Okay, if I take this particular chain of calls, this particular allocation pattern, then I'll get a race here, and then the same thing can be exhibited someplace else. So just like at the beginning, we had that one, probably an easier way to think about it is at the very beginning, we had that one example, which is with the lost update. Okay, even within that lost update, there were 4 different possible races. Really would correspond to one bug, logically in the program, but the reads and writes could race in multiple different ways. All right, and those will all get reported as separate races.
4 or 3?
3. 3 in that case, right? Because the read is not a race. Right. Right.
So what's
Sorry.
the code with 319 data race bugs?
Well, this is a huge program. This is a very, very big program. So in this case, it was, on average for each synchronization bug, there was like 3 different ways it could be exhibited, which is not unreasonable, right? So. Okay. All right, so developer feedback. So in JDTS, before we started this, we contacted them, and they said, as far as we know, there are no concurrency issues in this library. And then afterwards, they decided that they would overhaul how they did. They would overhaul how they did synchronization because they decided, there were 16 bugs, but those were actually fairly painful to fix. And it was just, they took it as a symptom of a deeper problem just with the organization of the whole approach to synchronization in that library. Huh? Yeah, I know. I'm close to the end here. And I found a bunch of bugs in Apache and 319 bugs in Derby. Okay, all right. Okay. So I already said quite a bit about the related work. And the main thing about static is, as you know, so again, to emphasize, race detection is actually a complicated property. Analysis of concurrency in general is a complicated property, made up of analysis of many small pieces. And it breaks down to several different analysis problems. Dynamic race detection is still the current state of the art. I think our tool, we hope that it will become the current state of the art actually as it gets out in one form or another for people to use. And the advantages, I think, over dynamic race detection is that it's going to be sound, it's going to find all the races for you, and it's also going to work with libraries. So I mean, the fact that you don't have to wait until you have a full program before you can start finding races in your finding concurrency issues in your code. All right, and then as just mentioned, shape analysis is another general area of related work. Generally, when people talk about analyzing shape, they're talking about much more expensive properties to compute about the heap than disjoint reachability. All right, so here's a summary of the contributions, and I already think I emphasized this enough. And since we're trying to wrap up, Mayur has great plans to go off and apply this to this basic idea to other things, and we're looking at things like transactions and atomicity. And here's there's other places where races are involved, but these are higher level properties where you want a race checker as one of the building blocks. And finally, thinking about if you can do effective race checking, how does this change the way you would design a language concurrent? How would you change the way you design a concurrent programming language to make it easier to write programs that are correct, concurrent programs that are correct in the first place? All right, and that's it. Thank you very much for your attention. And if we have time for a couple questions, I'd be happy to take them. So yeah.
So what do the false positives look like? Are there kind of common patterns?
So that's a good question, and I think I will let Mayur take that one. Do you want to answer that?
Well, if there's any logic that involves integers or booleans, so if you want to control synchronization using these kinds of the values of integers or the values of a boolean variable, and that is something where we don't have anything to do, because all this looks at is objects, that is object types, and not primitive data types. So that was the main reason for false positives.
Right. So
things like array indices, but again, that is the same thing as integers, speaking about integer values.
Right. So the question is, what do the false positives look like? And since our tool focuses on object-level reasoning, things that aren't objects sometimes confuse it, like integers and booleans.
There's actually somebody coming in right at 2, so I think
Okay.
we're going to have to stop. But maybe
That's
stick
fine.
around and answer
Yeah, I know. Happy to stick around for a few minutes and answer questions. Thank you very much.